Hi everyone, and welcome to calorimetry. So calorimetry is the process of measuring energy changes in a chemical system. So it's basically the lab process itself. We're just going to be using styrofoam cups to create a closed system. Not very exciting. And we're going to measure temperature changes of the surroundings that can be related back to the system. So the system and surroundings are connected to one another. So you can see up here the system, we learned how to use delta H for the system, and we also used Q for our surroundings, and now we're tying them together in an equation called a calorimetry equation. You'll notice this plus minus, and that just means that the two pieces, system and surroundings, are connected numerically but opposite in sign. So let me explain why that makes sense. If the system is giving heat off, the system would cool down while the surroundings got hotter. So the energy exchange between them would maintain the same value in terms of a number. For instance, the system could give 10 kilojoules of energy to the surroundings. The system would lose the 10, the surroundings would gain the 10. That's where that plus minus comes into effect. We're going to use that information in a moment. So this is our formula here. And you'll notice that the delta H, that is the formula for the delta H. And the Q, this is the formula for the Q. And so we can tie these together. So when we're working out a problem that is a calorimetry problem, we're going to see a delta T, and it's usually a large word problem. The left part of the equation is going to be reserved for information about the system, and the right-hand side is reserved for the surroundings. Rarely will the two cross over. However, there is an exception to that rule, and that's when we're using liquids. Because if we have container A being poured into container B, and they make a mixture now, when we're taking that temperature change, let's say I start with my thermometer sticking in the second beaker there, when I pour one into the other, they're now added together because the thermometer can't distinguish between the original particles that it could feel and the new particles being added. So there's an additive effect there, pardon me, with the surroundings when we deal with liquids. But typically they're two separate entities, so the solid and the surroundings will be kept separate. Now something that's a little important, and that is down here at the bottom. There are three assumptions that we use when we're doing calculations and working through calorimetry problems, and they can be found on page 309. I'm just going to read them to you and then I'll tell you why they're important. So the first one says that no heat is transferred between the calorimeter and the outside environment. Basically, we're going to assume that no heat is lost. We know that that's not true, but to do the calculations, we're going to make that assumption. The second point is any heat absorbed or released by the calorimeter materials, such as the container, are negligible. Because we're using styrofoam and it's a very good insulator, we can assume that not a ton of heat is actually absorbed by that material. And finally, a dilute aqueous solution is assumed to have a density and specific heat capacity equal to that of pure water. 1 gram per milliliter as a density and 4.18 joules per gram degrees Celsius or kilojoules per kilogram degrees Celsius as a specific heat capacity. That's the important one, as I've mentioned here, the third one. Because it means that when we're doing calorimetry problems, both in the lab and also on paper, so long as the solution we're creating is like water, we can assume it is water. This is important because when I have a mixture of water and something else, or if I make like a saltwater solution between an acid and a base, even though it's not pure water, it would be very hard to figure out what specific heat capacity to work with. So if I can assume it's mostly water anyways, then I can use the specific heat capacity of water, and the density part of things allows me to convert volumes to masses, as we saw in our lesson for Q. So a quick recap, remember the system is the reactant that's undergoing the change. So we can see sometimes with the language in the problem, the reactant is always on the delta HX side of the equation. So if they're asking for the enthalpy, molar enthalpy of the reactant, or the molar enthalpy of a substance, that's a clue that that is the system that they're talking about there. The other piece is the surroundings. So the surroundings, remember, is where the temperature change is occurring. And so think about where your thermometer is sticking. That's your surroundings. So often it's water, But remember, with two solutions, when I pour one solution into the other, I have to add those two solutions together because the thermometer will capture the temperature change of that entire volume. Some helpful hints when you're working out these problems. First of all, make sure you have matching units. These word problems have a lot of information in them because if you look at that formula, there are a lot of variables in a calorimetry question. So there's a lot going on. Make sure your units match. Second point for helpful hints is assumption number 3 is really important. When the product is a solution, you can assume that the density and the specific heat capacity of water is in play. So whenever it's a solution, which it pretty much always will be, you can use assumption number 3. So even if it's not water, you're going to assume it's water. Lastly, remember I talked about how the enthalpy and the heat have the same numerics, but they are opposite in sign. The last step is going to make sure that part translates. So when we do a calorimetry equation, the last step we're always going to do is we're going to always flip the sign of the final answer. This is going to make sure that we take this part into consideration, that as the system loses heat, the surroundings gain the heat. They're always going to be opposite in sign. So mathematically, we're going to solve the calorimetry question for whichever variable is missing, and the last step will always be flip the sign. Now that we've looked at some of the background, let's jump into a question together. So in a calorimetry experiment, 7.46 grams of potassium chloride is dissolved in 100 milliliters of water at an initial temperature of 24.1 degrees Celsius. The final temperature of the solution is 20 degrees Celsius. What is the molar enthalpy of the solution? So let's set up what we know and what we don't know. And I like to set it up underneath the equation and separate the pieces on the left side for system and the right side for surroundings. All right, so I've set my formula up in the middle, and on the left I'm writing stuff about the system, and on the right I'm going to write stuff about the surroundings. So again, going through the word problem again, it says in a calorimetry experiment, 7.46 grams of potassium chloride is dissolved in 100 milliliters of water. So my potassium chloride is going to be my system, and my water, my solution, is going to be my surroundings. Again, if I have a solid, it makes it easy. The solid will always be the system, and so by default, water is going to be the surroundings. And again, water is commonly the surroundings. So let's write down stuff that I know. So I have a mass of potassium chloride of 7.46 grams. I have a volume of water of 100.0 milliliters. I'm going to convert that into a mass straight away. Again, because the density of water is 1, I can assume that 100 milliliters is equivalent to 100 grams. I also know that T1 for water is 24.1 degrees Celsius, and my T2 is 20.0 degrees Celsius, and I'm looking for the molar enthalpy of the solution. So there's my question mark. So if I have a look at the stuff that I still need to get, I'm going to have to solve for moles over on this side. And on the right-hand side, I need a specific heat capacity still. And I also need to do a delta T calculation. Remember, it's always T2 minus T1. So I'm going to go ahead and, because it's water, I'm going to set up 4.18. And then again, because I have grams, I'm going to use joules per gram times degrees Celsius. Again, just making sure my units match one another. And then moles, I've got 7.46 grams times. Again, I'm looking for moles, so moles will go on top, molar mass will go on the bottom. I'm going to pause and I'm going to work out my molar mass right now. So for moles, my molar mass was 74.6, so I'm getting 0.100 moles. And the last thing I could do now is I can come over here with temperature. I'm going to have 20.0 minus 24.1. And I'll just remind you with decimal places, you're maintaining lowest decimal places, so 1 decimal place in this case, and it's going to be a negative 4.1 degrees Celsius. So we've got all the pieces that we need now. So my job is going to be to rearrange to solve for delta Hx. So I'm just going to bring n to the right-hand side because it's multiplying. When I bring it over the equals, it's going to divide. So I'm going to substitute and solve. So I've substituted in, and when I solve, I get negative 171.38. And I'm just going to have a quick look at the units, so I will notice that grams will cancel out, my degrees Celsius will cancel out, and I'm going to be left with joules per mole here as my unit. And now I want to consider my significant digits. I want to bring it down to 2 significant digits based on my temperature here. And I also want to remember the important step of flipping the sign. And there's a way to check to make sure we do this and it makes sense, but let's put it all together and then I'll go through that. So my final answer will be positive 1.7 times 10 to the 4. Ooh, that's not a 10. Times 10 to the 4 joules per mole. You could also convert it into kilojoules per mole if you wish. That's fine too. So the flipping of the sign, let's see what this means. And this is where you can sort of check your work. Positive, remember, means endothermic. And endothermic means it's getting cooler. If I go back to the temperature change that I had in the beginning, I started with a temperature of 24.1 degrees Celsius, and it went to a temperature of 20.0 degrees Celsius for T2. So this is cooling, which means it should be endothermic. And again, this is why we flip the sign no matter what with calorimetry, no matter which piece I'm solving for, that's always the last step, because the system side and the surrounding side are always the same number, but opposite in sign. So flipping the sign at the end will make sure that part turns out correctly. So challenge time means I want you to try this by yourself. So I'm going to read it to you, but then I want you to pause the video and I want you to try to solve it on your own. And then when you think you got it, I want you to press play and see if you got it. So what volume of water could be heated from 14.2 degrees Celsius to 27.8 degrees Celsius if 3.87 grams of propane were heated, having a molar enthalpy of negative 2,043 kilojoules per mole? Lots of stuff going on here. You're going to set it up the same way I did. Start with the formula, decide whose system and surroundings, start putting values on left and right side, pull any values that you can get from other places, and then solve away. So time to pause and see what you can do. So hopefully you paused and hopefully you got at least to this stage at a very minimum where you figured out that the system is propane and the surroundings is water. And then we have a mass of propane and a delta HX, or molar enthalpy of propane, so that's going to go on the left. On the right, we're looking for volume of water. Now, of course, because there's no volume here, we're going to take that volume at the end and we're going to convert it into mass using density of water as 1. So kind of the reverse of what we did in the last question. We have a T1 and a T2. And just like the last question, there are a few pieces that I can get now before I do anything else. So for instance, I can find my delta T, T2 minus T1. I can get my specific heat capacity for water, 4.18. In terms of units here, if I have a look over on this side, the delta HX is in kilojoules per mole. So I'm going to use kilojoules per kilogram degrees Celsius. Otherwise, I'm going to get into, I can't make a dot, jeez. I'm going to get into trouble when I try to connect the units later on. And you might be thinking, but what about this grams? Well, this is a mass, and I don't want that as mass. I want to turn that into moles. So that mass is going to disappear anyways, so 1 mole over molar mass. Now this is where we don't have any organic chemistry under our belt, so we don't know necessarily what the formula of propane looks like. So this is where we use, Google. So you want to look up the formula for propane, figure out what it looks like, and then come up with a molar mass. All right, so I have worked out the amount of moles. The formula for propane was C3H8. And then I also worked out my temperature on the other side. So at this point I have everything I need, and I'm going to rearrange the formula to solve for M so I can convert it back into a volume afterwards. So here's my rearrangement, and then I'm going to substitute and solve. So at this point I can just go through and solve for the math. So I'm getting 3.15175, etc. In terms of units, I've got moles and per mole. I've got kilojoules and kilojoules, and this is why I said you're going to have to match your unit based on that. I've got degrees Celsius and degrees Celsius. Sorry, my bad, that's a negative because of the negative here. And the only unit remaining is kilograms, which makes sense because this is a mass. Now, I was asked to solve for volume, but because the density of water is just 1, and I know that there's a relationship if I solve for V, mass over density, our mass is going to be flipping the sign, so flip, let's write that down, we want to flip the sign as our last step as always, so we're going to have a positive 3. Significant digits wise, we're limited to 3 digits, so 1, 5, and then finally we have kilograms, and then we want to convert, so again 3.15 kilograms. The density of water is 1 kilogram per liter, so this is going to be the equivalent of 3.15 liters. That's my final answer. A little bit tricky, lots of stuff going on for that one. All right, we have one more challenge. So again, I'm going to read it to you, then I want you to pause and attempt it on your own, and then replay it and see how well you did. So solution A has a concentration of 0.65 moles per liter and a volume of 35 milliliters. It's poured into 650 milliliters of water, and the temperature goes from 22.1 degrees Celsius to 14.9 degrees Celsius. What's the molar enthalpy of solution A? So at this point I want you to pause and then play it to see how you did. So this one can be a little bit tricky because there's no solid here. We have 2 solutions, but there's a couple of clues to help us out. So first of all, solution A seems to be a little more important than water. Water has consistently been the surroundings. So that's one clue for us for this one, as solution A is system and water is the surroundings. Another clue for us is that it asks us what's the molar enthalpy of solution A. Molar enthalpy is on the system side, so that's another clue that solution A is the system. Another clue is that water is where the temperature change is happening and temperature change is on the surrounding side. Now there is going to be a trick to this, and we talked about it up front in this lesson, and that is we have to consider the entire volume of the 2 things being mixed. So let's see how that would work out. But let's first start by looking at what do we know and where should it go. So on the left-hand side for the solution A, we have a concentration of 0.65 moles per liter. Because it's a solution, we have different types of information being given here. A volume of 35 milliliters, and it's poured into 650 milliliters of water, and the temperature goes from 22.1 degrees Celsius to 14.9 degrees Celsius. And we want to know what the molar enthalpy is of our solution of solution A. So a couple of things that we have to consider here. On the left-hand side, we're going to use C and V, and we're going to solve for moles. Now, moles, we're going to use a little bit different. We're going to use our C equals N over V. We're going to use solution chemistry since it's a solution. So we're going to do N equals C times V. I'll also remind you here that concentration is always moles per liter, so we do have to convert our milliliters into liters here as well. So we've got 0.65 moles per liter times 0.035 liters. Let's come up with a number. So I'm getting 0.02275 moles there. I'm just keeping some extra digits. On the right-hand side, there's a couple of things I can do as well. So again, I'm going to pour solution A into the water. The thermometer, the delta T that I see here, the temperature change that's going on, that's going to measure the entire volume. So what I have to be mindful of is that I have to add that extra bit of information in here for a grand total of all of the particles in the final volume, because of course the thermometer doesn't know the difference between the water and solution A. It's going to be measuring the temperature change of both pieces. So they're going to be additive. So I've just added those pieces, so the volume is additive, we've got a temperature change, and finally we can add our specific heat capacity. Even though it's not going to be pure water, it's going to behave like water. Using assumption number 3 of calorimetry, things that are mostly water are just going to be assumed to be water, so 4.18 as per usual. And just looking at the parts here, one thing I forgot to do is, because I don't want to use volume, I'm going to convert this into a mass. Milliliters are equivalent to grams using density. And because that's grams, when I use my specific heat capacity, I'll pull the joules per gram degrees Celsius as the unit. Why can't I make dots today? And so I'll use that So lots of things going on for this one, a little bit different than the other two. But now that we've got all the working parts worked out, we can put this together quite quickly. All right, so at this stage I'm getting negative 906,187 and some extra stuff. And in terms of units, let's cancel some stuff out. So grams can go, degrees Celsius can go, and I'm left with joules per mole, which makes sense since this is a molar enthalpy. And in terms of significant digits, I want to keep 2 significant digits. And of course, my last step always is flip sign. So I'm going to put all those pieces together to get a final answer of positive 9.1 times 10 to the 5 joules per mole. So now it's time to practice. We need to be able to do this for word problems, and we also need to be able to do it in a lab setting with real data, and we need to be able to work it out no matter which piece I'm looking for, what the units are doing, all of that good stuff. So time to practice to become experts.